We've seen a few existence results for ordinary differential equations and also uniqueness results. And those results were the Peano existence theorem and the Picarlinolf theorem. Now, these existence and uniqueness results guaranteed the solution for some initial value problem starting at some time t0 and then up to some fixed time tau. And then up to some time tau. So we've seen some examples of initial value problems where the solution only existed for some time until maybe the solution became infinite, developed a singularity, or maybe the slope of the solution became infinitely steep. But we've also seen some initial value problems where the solution existed for every time. We start with some time t0, and then the system can be extended for arbitrary long times. In fact, the vast majority of initial value problems that we had a look at fit into that category. And it turns out there's actually an existence and uniqueness result which quite often can be used to show the existence of a solution to an initial value problem that extends to arbitrary long times. So let's have a look at the following. Suppose we've got a real number t0 and a vector y0 in R to the n. And let us suppose that f is a continuous function which takes a real number and a vector in R to the n and which outputs another vector in R to the n. And let's furthermore suppose that it satisfies the following condition, namely there exists a number L greater than 0 such that for all times t and for all vectors y1 and y2 from R to the n, we have that the distance of fty and fty2 is bounded by L times the distance of y1 and y2. Formally, the Euclidean norm of fty1 minus fty2 is bounded by L times the Euclidean norm of y1 minus y2. If that condition is met, then there exists a differentiable function y, which is defined at t0 up to infinity, which maps into R to the n, and which solves the initial value problem where yt0 is equal y0, and y prime of t is equal f of t and y of t for all times t after t0. And that solution is unique. So if you've got an initial value problem, okay, in order to apply this result, we need to take a look at f, and then we check whether it is defined for all times t and vectors y. So if f is defined for all possible inputs, and if it satisfies this inequality here for all times t and all possible choices of vectors y1 and y2, if that is satisfied, then we know that this initial value problem yt0 equal y0 and yt and y prime of t equal f of t, y of t has a unique solution which exists for all times after t0. It does not blow up and it does not develop any singularity, and the derivative never becomes infinity. We can apply that result to quite a number of initial value problems that we already know. So let's suppose we've got y prime of t equal alpha times y of t, and as initial condition we just say, okay, why not, let's say y0 is equal 1. In that example, the right-hand side of the ordinary differential equation can be written as fty defined as alpha times y. Okay, certainly this is defined for all t and y. It's also continuous. And we need to check this inequality. So we want to show that there exists L greater 0 such that for all times t, the real numbers for any time, and let's say for all y1 and y2 from the real numbers, we have that fty1 minus fty2, the distance between those two numbers is bounded by L times y1 minus y2, L times the norm of y1 minus y2. And that is actually, well, extremely easy in this case. Namely, we have alpha y1 minus alpha y2. Okay, this can be bounded from above by the absolute value of alpha times the absolute value of y1 minus y2. So in this case, the constant alpha can serve as my L. So this purely theoretical result tells me that there exists a unique solution starting at 0 and going on to infinity of this initial value problem. In fact, this also agrees with what we already know about this differential equation, and namely we remember y of t the solution has the explicit formula exponential of alpha t. And this completely agrees what we already know about this ordinary differential equation. So this theoretical result shows the existence of a solution which also agrees with what we already know about this differential equation. So it seems that the result is quite powerful. This differential equation, after all, is very simple, has an explicit solution that we already know, exists for all times t, and the theoretical result is strong enough to recover the existence of a solution for all times in this special case here, for that special differential equation. So this indicates that the result is actually quite powerful. Let's have a look at another initial value problem. So we've got the differential equation y prime of t equal 1 over t squared plus 1 y of t plus the sine of y of t with initial condition y0 equal 1. Let's again write down the right-hand side. So we identify that we have the function f of ty equal 1 over t squared plus 1 times y plus the sine of y. Okay, it's defined for all t and y. It's continuous. So we need to check this condition. So we need to check that to apply this global existence and uniqueness result, we need to check that there exists L greater 0 such that for all t from the real numbers and y1 and y2 from the real numbers, we have that the distance of ft y1 and ft y2 is bounded from above by L times y1 minus y2. And this constant L should not depend on the time t and should not depend on y1 and y2. Okay, this can be done as follows. So let's take 1 over t squared plus 1 times y1 plus sine of y1 minus 1 over t squared plus 1 times y2 minus sine of y2. So it seems like a good idea to group these terms and apply the trying inequality. So we bound this from above by the absolute value of 1 for t squared plus 1 y1 minus 1 over t squared plus 1 times y2 plus absolute value of sine of y1 minus sine of y2. Okay, so what we see in the first term, we can factor out the absolute value of 1 over t squared plus 1 times y1 minus y2. We're going to work with that. And also, in the second term, well, one possibility is to write this as an integral. The absolute value of the integral from y1 to y2 cosine u du Okay, so now going from there, on the one hand, this term here, 1 over t squared plus 1. Okay, that can safely be bounded from above by 1. So we already have y1 minus y2. And then on the other hand, okay, this integral can be bounded from above by the integral from y1 to y2 of the absolute value of cosine u du. And of course, this can also be bounded by just 1 times the distance of y1 minus y2. The maximum value of the absolute value of the cosine is 1. Putting this all together, I can bound this from above by 2 times y1 minus y2 absolute value. Particularly, this is my constant L. So, and the conclusion is there exists a unique solution y which starts at 0 and goes on to infinity. I would like to remark that this ordinary differential equation was nonlinear because it involved sine of y of t. And even though we do not know the exact solution, maybe there does not even exist a formula for the exact solution, we know that it exists for all times. And this can be shown also for arbitrary starting values. I've not used the precise starting value. Okay, let's take a look at yet another ordinary differential equation that is nonlinear. So we got y prime of t equal y of t over 1 plus y of t square. And the initial condition this time is y1 equal 2. The initial condition itself actually doesn't matter. It could also be y0 equal 5 or y minus v equals 7. So we identify in the Cauchy formulation of this initial value problem, we have f of ty equal y over 1 plus y square. In particular, we see it's an autonomous problem. And okay, check that f is defined for all t and y. And we check that f is continuous. So it remains to check in order to get this existence and uniqueness result for all times that there exists L such that for all times t and y1, y2 from the real numbers, we have that the distance of ft_y1 and ft_y2 is bound from above by L times y1 minus y2, an absolute value. Okay, this looks a bit difficult because of this nonlinear structure of the function f. We can tell it does not depend on the time t, but the dependence on y looks a bit complicated. So let's just try and see what happens. I plug in y1 over 1 plus y1 square minus y2 over 1 plus y2 square and takes the absolute value. The result is a bit tricky, but it is possible. So one promising approach is to again use the fundamental theorem of calculus. So we write this as an integral from y1 to y2 of the derivative of the function f in y, and then we try to bound the derivative. Let's try that. We bound this from above by the absolute value of the integral from y1 to y2 of the derivative of f in y, which can be written as follows, namely, let's take 1 plus y squared minus y times 2y over 1 plus y squared to the square now, del y, absolute value. Let us simplify that a little bit. So this is the same as the integral from y1 up to y2 of the function 1 minus y squared over 1 plus y squared squared del y. We take the absolute value of that. Now we would like to know that this integrand here is bounded in terms of absolute value. In fact, there's an argument to see that this integrand in fact is bounded. So there actually exists a constant such that the absolute value of the integrand is bounded from above by that constant, which we call L. I'll come back to that in a few moments. And then we get the entire thing is bounded from above by L times y1 minus y2 absolute value. Now, why does this constant L exist? On the one hand, we see if the absolute value of y gets very large, then the denominator of this fraction is going to be much larger in magnitude than the numerator. So as y has a very large magnitude, this fraction is going to converge to 0. So there's some threshold where the numerator stays smaller than the denominator. So outside the threshold, this fraction will be smaller than 1. And inside the threshold, okay, it will assume some maximum value, which we call L. So whatever this maximum value is, we know that this fraction essentially is bounded for all y, no matter how small or large y is. In fact, if you actually want to compute this maximum value explicitly, you can use tools from calculus to find the critical points of this integrand. And then you can find that L is in fact equal to 1. But that's more of a bonus here in this context. Okay, with that in mind, we can apply this existence and uniqueness theorem, and we get that there exists a unique solution a unique solution, y which starts at 1 in this example and goes up to infinity. A unique solution y, which is defined for all times from 1 to infinity, and this solves the initial value problem. And again, instead of 1, I could also choose initial time 3 or initial time -5. That really doesn't matter. Let's take another look at the differential equation y prime of t equal y of t square with initial condition y0 equal 1. We've seen that differential equation before, and we remember the solution perhaps, namely the solution is the differential equation with these initial values is y of t equal 1 over minus t. So in particular, the solution becomes singular in finite time. And we will see that indeed this differential equation does not satisfy the conditions of the global existence in uniqueness theorem. So let's recall the right-hand side can be written as f of ty equal y square. Okay, it is defined for all t and y. It is continuous. But now the question is, does there exist L greater 0 such that for all times t and y1, y2, we have that f of t y1 minus f of t y2 is bounded from above by this constant L times, in absolute value, bounded from above by this constant L times the distance of y1 and y2. Unfortunately, that's not the case. So the answer is no, there does not exist L greater 0 such that for all real numbers t and y1, y2 from the real numbers, we have that y1 square minus y2 square is bounded from above by L times y1 minus y2 in absolute value. So this function fty is just the square of y. So this does not look particularly threatening, but it does not satisfy this continuity condition, this particular continuity condition that ensures that ensures that any solution exists for all times. And this perfectly fits in line with our observation that the solution to that initial value problem develops a singularity in finite time. So how do we see that this constant L does not exist for this inequality? Now let's just see that when y1 and y2 are different, then this can be written as y1 square minus y2 square in absolute value divided by the absolute value of y1 minus y2 should be bounded from above by some constant L. But that just means that the slope of the quadratic function which maps y to y square is uniformly bounded, or is bounded over all real numbers. But that is not the case. So this constant L does not exist. This can actually be seen by a small using a small graphic. If I graph this function y mapping to y square, then I see that, okay, if I take 2 points on as inputs, let's say y1 and y2, and I try to find the slope of the secant through the graph at y1 and y2, then as I move y1 and y2 further and further apart, the slope of that secant actually becomes infinitely large. So such a constant L cannot exist. I can always find y1 and y2 such that this quotient here becomes as large as I want. So the conclusion is the conditions of the global existence and uniqueness result, global existence and uniqueness theorem, are not satisfied. So the existence of a solution for all times is not guaranteed. For all times does not follow. And indeed, the differential equation, the solution of the differential equation can develop a singularity in finite time. Indeed, the solution of the initial value problem is defined only for a finite amount of time. Before it blows up. That's actually great. So it shows us that we have at least one example where the theorem does not apply. This always sets us on the right track to what actually happens. I figured I might discuss another ordinary differential equation. So let's take a look at the following ordinary differential equation, namely y prime of t equal 1 over 3 minus t multiplied with 1 over 2 minus y, together with the initial condition y naught equal 1. So this is a first order differential equation. Okay, we have seen several abstract formulations for ordinary differential equations. And one example was the form f of t, y of t times y prime of t equals 0. And in this case, f can be written as f of t, y, and y prime. It takes the time variable and two more variables corresponding to y and the first derivative of y. And this function f is defined as y prime minus 1 over 3 minus t times 1 over 2 minus y. As you also recognize, this differential equation is not linear, and it's also not autonomous, so it doesn't really have much structure. But it is a differential equation that actually is in the form of a Cauchy initial value problem. So it's an instance of a Cauchy problem. And in particular, so it's in the scope of the ordinary differential equations that we cover in this class. So within the framework of the Cauchy initial value problem, or Cauchy problem, this differential equation can be written as y prime of t equal f of t and y of t, where this function f takes the following form, namely f of ty is equal 1 over 3 minus t times 1 over 2 minus y. So it has a form of the Cauchy initial value problem, and we can understand a bit about the solution properties of this ordinary differential equation by taking a look at the function f in the Cauchy problem. Also, I would like to bring to attention that this ordinary differential equation is separable. So if you remember this from your calculus classes, you might actually remember the separation of variable technique, which allows you to explicitly solve this initial value problem. Now, let's discuss the application of the piano existence theorem. The solution properties of that initial value problem can be illustrated with a small picture. So we have the ordinary differential equation y prime of t equal 1 over 3 minus t times 1 over 2 minus y, with initial condition y at 0 is equal to 1. And in this picture here, you see a horizontal axis, which is for the time direction, and a vertical axis, which is for the y direction. So let's first have a look at the right-hand side of this initial value problem. So we've got the expression 1 over 3 minus t times 1 over 2 minus y. So that expression is not defined when t is equal to 3 or when y is equal to 2. So in this coordinate system, in this ty coordinate system, I've indicated in red the areas where the right-hand side is not defined. So we have got the t equals 3 axis and the y equal 2 axis. Okay, so the function f of t and y is not defined in this red area. Now, we try to understand how the Uniqueness existence theorem is applied. First, let us mark the beginning. So the initial condition is y of 0 equal 1. So we have got t naught equal 0 and y naught equal 1 in the formulation of the piano existence theorem.
Let's mark this in the coordinate system, that point. From that point, any solution will, so to speak, walk to the right in the positive time direction and will move up and down, depending on the differential equation. Okay, we certainly don't want to run into this red area as the graph evolves in this coordinate system. So on the one hand, we want to have some distance in the time direction from the red area, and we also want some distance in the y direction from the red area. We want some distance in the time direction from the red area so that we can actually move forward in time, which I think is quite understandable. And we also want some distance from the red area in the y direction so that actually the point can evolve a bit. Okay, for the Piano existence theorem, I need to pick some time after t0, some time t1, and I'll simply pick t1 equal 1. Okay, so the time interval is length 1. And then I also need to pick some rho. And I take an interval in the y direction centered at y0 equal 1 with the radius rho. So, and I should take the number rho small enough so I don't hit the red area here. Okay, one possibility could be rho equal 1/2. Okay, so that gives me my interval on the y direction. And for the Piano existence theorem, I take a look at the time interval times the y interval. Take a look at that shaded area here. The initial value problem does have singularities. It does not have any singularities here in this blue shaded area. So in particular, within the blue shaded area, the function f(ty) is continuous. Now the Piano existence theorem tells me that there exists a solution, at least for some period of time, and that solution, I can move forward a bit forward in time, and the solution will not hit the red area. That is what the Piano existence theorem tells us. As you can tell, those are pretty mild conditions. Typically, you can determine quite easily for which values of t and y the right-hand side is not defined. And it's easy to find, typically, given some initial condition, it's easy to find some area that does not touch the inadmissible area. It is easy to find some time interval after t0 and some environment around y0 such that this rectangle will not overlap with the red area where f is not defined. In fact, the solution does not exist for all times t. If you plot the function, what you're going to see is that the solution is going to evolve forward in time, and the graph of y, as we get close to some point after t equal 1, the graph is actually going to explode to infinity. So the function evolves and then gets infinitely steep, and as we reach some particular time after t equal after 1, the function goes vertically up to infinity. So in particular, so to speak, as the function gets closer and closer to this point in time, the derivative becomes infinite. And eventually we hit this red shaded area here. The Peano existence theorem tells us that there exists some time tau greater than 0 and a function from 0 up to the value tau, mapping into the real numbers, such that y is differentiable and the pair t and y of t is in the domain of f, which only means that t is not equal 3 and y of t is never equal 2. That's all what it means. So we stay within the area where f is actually defined. And we've got, well, the initial condition, y of 0 is equal 1, and the differential equation is satisfied. Y prime of t is equal f of t times y of t for all times t between t0 and tau. We have found a rectangle where the right-hand side of the initial value problem fty is continuous, and essentially we only need to stay away from the singularity area. You only need to stay away from those points where f is singular. So as long as the rectangle keeps a distance from the red area, we are fine. We have a continuous function f over that rectangle, and we can apply the Peano existence theorem. In fact, even more is true. We can also apply the Picarlinolf theorem. So let's have another look at that. We've got y prime of t equal f of t y of t with y0 equal 1. And in the Peano existence theorem, for the statement, we had t0 equals 0 and t1 equal 1. And the initial value was y0. And we take a radius rho of 1/2 around the initial value. What we try to find is a constant L with the following inequality, namely f of t y1 minus f of t y2, takes the absolute value, is bounded from above by L times the absolute value of y1 minus y2. And that is true for all values t between t0 and t1, which means all values t from 0 to 1. And it is true for all y1, y2 taken between y0 minus rho and y0 plus rho, which concretely means that y1 and y2 are taken between 1/2 and 3/2, are taken from 1/2 up to 3/2. So plugging in the definition of f, what I want to show is that 1/3 minus t times 1/2 minus y, 1 minus 1 over 3 minus t times 1 over 2 minus y2. The difference and takes the absolute value is bounded from above by some constant L times the absolute value of y over 1 minus y over 2. Okay, let's take a look. So I have this difference here, and I can factor out the absolute value of 1 over 3 minus t. And I'm left with the product I'm left with the absolute value of 1 over 2 minus y1 minus 1 over 2 minus y2. This function, 1 over 2 minus y, is differentiable as long as I stay away from the singularity at y equal 2. So I can again apply the fundamental theorem of calculus. For this last part. And I get that's the same as the absolute value of the integral from y1 up to y2 of the derivative of the function, which happens to be minus 1 over 2 minus, let's say, 2 minus z to the square dz. Okay, and that term can be bounded from above by the following, namely the maximum of z between 1/2 and 3 over 2 of the absolute value of 2 minus z to the minus 2 times the distance y1 minus y2. Okay, let's put this all together. The conclusion is as follows. You've got 1 over 3 minus t times 1 over 2 minus y1 minus 1 over 3 minus t takes the absolute value of that. And it's bounded from above by, well, the maximum of t between 0 and 1 of 1 over 3 minus t times the maximum of 1/2 of z between 1/2 and 3 minus 2 put into the function 2 minus z to the negative 2 times y1 minus y2. Okay, let's take a look at the first term here, the maximum over t. Well, this you can easily see this term is actually largest if t is largest, if t is closest to 3. So we get that this term is bounded from above by 1/2. On the other hand, this maximum here in z, it is largest if z is closest to 2, which happens to be the case if z is equals v over 2. So we've got 1/2 to the negative square, which gives us 4. We conclude that the entire thing is 1 from above by 2 times y1 minus y2. And that too is my constant L. So in addition to the Peano existence theorem, we have that the Picarlinolf theorem applies. The Picarlinolf theorem tells us now the following, namely the solution is unique.
Let's take a look how our framework applies to systems of ordinary differential equations. Well, one important example for a system of ordinary differential equations is the harmonic oscillator equation. Let's recall we had x prime prime of t equal negative omega square times x of t, where omega is a positive parameter. And we had initial conditions x0 is equal x0, the initial condition for the position. And we had the initial condition for the velocity x prime at 0 is equal y0. Here x is the unknown function, the dependent variable, and t is the independent variable. The harmonic oscillator equation is the second order, it's autonomous, and it's linear. Let's just check how this fits into our abstract definition of linear ordinary differential equations. So we can rewrite this equation as 1 times x prime prime of t plus 0 times x prime of t plus omega squared times x of t equals 0. In this context, the coefficient for the second derivative is 1. It's our coefficient a2, using the terminology from the definition of linear ordinary differential equations. The coefficient a1 of the first derivative is just 0, and the coefficient a0 of the function itself is omega squared, of course. Using our abstract definition of ordinary differential equation, we can write this equation also as f of t, x of t, x prime of t, and x prime prime of t equals 0, where f is the following function, namely f takes t, x, x prime, and x prime prime, and equals x prime prime plus omega square x. As you can tell, the equation is indeed autonomous because t does not enter the definition of f actually. Now, we would also like to rewrite this as a system of ordinary differential equations, and we remember that we did so by introducing an auxiliary variable for the velocity. So let's define y of t equal x prime of t, from which you conclude that, well, the derivative of y of t, the derivative of the velocity, is just the second derivative of x, the acceleration. And from the ordinary differential equation, we get that x prime prime of t is equal negative omega squared times x of t. Okay, if we put all that together, we see that we can rewrite the harmonic oscillator equation as x prime of t equal y of t, and y prime of t equal negative omega squared times x of t. Okay, that system now is first order. It is still autonomous, and it's also still linear. In fact, we can write the system as a Cauchy problem now, simply by putting x of t and y of t into a vector variable. So we define u of t as x of t, y of t. It's now a two-dimensional vector. The first variable is the first entry is the position, and the second entry of that vector is the velocity at any time t. We also take the initial values x0 and y0 and put them into a vector u0. Now, to put the ordinary differential equation into the framework of Cauchy problems, we define a function f of t and u. This function f takes a time variable t, that's just a real number, and takes a vector variable u, a two-dimensional vector. And the output of f is another two-dimensional vector. Namely, the first component of the vector is the second component of u. The second component of the new vector is negative omega squared times the first component of u. In other words, the first component is the y-coordinate of u, and the second coordinate of the new vector is just the first coordinate of u multiplied with negative omega squared. And if you take a sharp look, you actually recognize that you can rewrite this as a matrix vector multiplication. Namely, let's put up a matrix of size 2 times 2. The first row is 0, 1, and the second row is negative omega squared, 0. And we multiply this matrix with the vector u, just the two-dimensional vector with ux and uy as coordinates. So in particular, f of tu can be written as a matrix vector product with fixed matrix with fixed 2 by 2 matrix applied to the vector u. Without this definition, we see that we can reformulate the harmonic oscillator equation as a Cauchy problem, namely u prime of t equal f of t u of t, with initial condition u at 0 is equal u0. Let us practice how we can apply the different uniqueness and existence theorems to that Cauchy problem. Let's start with how to apply the piano existence theorem. So we got u prime of t equal f of t u of t, where f of t and u is defined as the matrix vector product with the 2 by 2 matrix, 0, 1 in the first row, and negative omega squared 0 in the second row, multiplied to the vector u. So we start at time t0 equals 0 with initial vector u0 equal x0 and y0. The initial vector contains the initial position and the initial velocity. Okay, to apply the piano existence theorem, we also need to pick an end time. We go from time t0 up to time t1. And we also need to pick some radius rho around the initial vector u0. In this case, you can pick some completely arbitrary, since the function f is defined everywhere. So in particular, just formally, we check that f is defined for all pairs of times t and vectors u, where t is taken from the interval that goes from t0 up to t1, and u is taken from the ball of radius rho around the vector u0. I've made a small picture of that ball here. And we also check that f is continuous, which certainly is the case, since every entry of the output vector of f is continuous. Now, the Peano existence theorem tells us that there exists a function u, which lives on some time interval that goes from t0 up to tau, where tau is some time after t0, and takes values in r to the 2, such that u of 0 is equal u0, the initial condition, and u prime of t is equal f of t u of t. So in particular, the Cauchy problem has a solution which lives for at least some time. So if we try to put this into an illustration, I have a time t that starts we have a function that starts at u0 at time t0, and then it moves from u0 along some trajectory over time. I think it's intuitive that we need some radius around u0 in general. Some ball around u0 which stays in the domain of f, so that we have some room where this function can actually evolve. The Peano existence theorem guarantees the existence of a solution, but it does not necessarily guarantee the uniqueness of that solution. So there might be many different solutions. But, as we know, the harmonic oscillator equation has a unique solution if we provide initial conditions for position and velocity. And in fact, this is also supported by our abstract theory. Namely, we can apply the Picarlinolf theorem. The only thing that we need to check now as for this extension of the Peano existence theorem is that there exists a constant L greater than 0, such that for all times t from this interval t0 to t1, and for all vectors u1, u2, taken from this ball of radius rho around u0, we have the following inequality, namely the Euclidean distance of ft u1 and ft u2 is bounded from above by L times the Euclidean distance of u1 and u2. Formally, the Euclidean norm of ft u1 minus ft u2 is bounded from above by L times the Euclidean norm of u1 minus u2. One could say that if I take two different values for the second variable, like u1 and u2, then the variation of f is at most proportional to the variation of the second variable. Okay, let's try to prove that inequality. That's not very difficult, actually. So, just writing down the definition of f, we take the Euclidean norm of the difference of two matrix vector products. So we take this matrix 0, 1, negative omega square, 0, and multiply it with the first vector u1, and we subtract the same matrix applied to the second vector u2. Now remember that matrix vector multiplication is linear in the vector, and so we can summarize this as follows. Namely, we take the Euclidean norm of the matrix vector product with the matrix 0, 1, negative omega square 0 multiplied with the following vector, namely the first component is u1x minus u2x, and the second component is u1y minus u2y. Since the matrix is so simple, we can simply compute this matrix vector product, and then we take the Euclidean norm of the vector with first entry negative omega square times the difference u1x minus u2x, and the second entry is u1y minus u2y. With some knowledge from linear algebra, or maybe some explicit calculation of this Euclidean norm, we can see that this is actually bound from above by the maximum of 1 and omega square multiplied with the vector u1y minus u2y and u1x minus u2x. And as it happens, this is actually bounded from above. In fact, it's equal to the maximum of 1 and omega square multiplied with the Euclidean distance of u1 and u2. So the conclusion is that this constant L that we have tried to find can be picked as the maximum of 1 and omega square. In particular, the Picarlinolf theorem applies, and the conclusion is that the solution is indeed unique. So remember that the harmonic oscillator had a unique solution, and in fact, that solution could extend to infinite time. That solution exists for all times, and this is actually covered by our abstract global existence and uniqueness theorem. That is now quite easy to check. Emily, we have already seen that f is defined everywhere and it is continuous. And we have proven this inequality, the Euclidean norm of ftU1 minus ftU2 is bounded from above by L times u1 minus u2 in Euclidean norm. We have found this constant L already, and that is true for all times t and all vectors u1, u2, taken from the two-dimensional Euclidean space. And the conclusion is that there exists a unique solution for all times t. The solution exists for all times starting at 0, going up to infinity, and it satisfies the initial condition u of 0 is equal u0, and the differential equation u prime of t is equal f of t and u of t for all times t after 0. I would like to bring conserved quantities back to your memory. So we know that there exists a quantity called the energy for any combination of position and velocity. And the energy of position x and velocity y is defined as 1/2 y square plus 1/2 omega square x square. The first term, 1/2 y square, corresponds to the so-called kinetic energy, the energy that is stored within the velocity, and 1/2 omega square x square corresponds to the potential energy, the energy that is stored in the position, so to speak. And we have seen that the energy of the harmonic oscillator remains constant over time. So if I take the position variable x of t and the velocity variable y of t and put this into the energy, okay, this defines the energy dependent on time, and it remains constant. For example, if I take a look at the initial position and the initial velocity, x0 and y0 at time t equals 0, then I can explicitly compute the energy of the system at the initial state, and I know that throughout the entire evolution of the system, this energy remains constant. One way of putting that is, if I take the energy of x of t and y of t, and of this function I take the derivative in the time, then the time derivative of that guy is 0. What you see here are a few computer-generated plots which illustrate the position and velocity dynamics of the harmonic oscillator. Let's suppose I start the harmonic oscillator system with initial position 0.1 and initial velocity 0.2. And as for omega, we pick the square root of 2, so that omega square is just 2. And I let the system run for 15 units of time. So on the left, you see the graphs of the position and velocity variables as they evolve over time. And you can clearly see that the system oscillates. The blue curve is the position variable, and the orange curve is the velocity variable. Now let's take a look at the picture on the right. On the right, the x-axis corresponds to the position variable, and the y-axis corresponds to the velocity variable. Now let's suppose I start with my initial position and initial velocity. So 0.1 and 0.2. Now let's suppose I keep track of the x and y coordinates as they evolve over time and use this to draw a curve within the xy coordinate system. Let this system evolve, and since the system is periodic, the curve will eventually come to its own end again. This is why you see a closed curve here. So in some sense, the oscillator will describe a circle in the xy plane. It turns out actually, the circle here is precisely a level set of the energy function. So if I take 1/2 y square plus 1/2 omega square x square, then along this curve here, the energy remains constant. And as you can tell, this is an ellipsoidal shape. Along this ellipsoidal shape, the energy remains. This ellipsoidal shape describes a level set of the energy function. This graphic was actually produced with a numerical method that is specifically designed to preserve such conservation laws in numerical simulations. It's quite an active topic of research. I spent 6 months in a research program last year about this topic.
Now let us have another look at the Lotka-Volterra system. We fix constants alpha, beta, gamma, and delta larger than 0, and take a look at the following initial value problem. We have x prime of t equal x of t times alpha minus beta y of t, and y prime of t equal y of t times gamma x of t minus delta, with initial conditions at time t equals 0, x0 equal x0 and y0 equal y0. This is a first order system of ordinary differential equations. It is also in the formulation of a Cauchy problem. We see that this is a nonlinear problem, and we also see that it is autonomous. If we put it into the abstract framework for ordinary differential equations, then we need to work with a vector variable. So let us define u of t equal x of t, y of t in a vector. The initial condition is u of 0 equal x0, y0. And the ordinary differential equation can be written as f of t, u of t, y prime of t equals 0, where f of t, u, and u prime is the following vector, namely the first component is u prime x minus ux times, in brackets, alpha minus beta uy, and the second component is u prime y minus uy times ux minus delta. So the function f takes the time variable, the vector u and the vector u prime, and maps this to another vector. If we put this into the form of a Cauchy problem, we can also rewrite this as u prime of t equal some function f of t, u of t, where this new function f of t and u is defined, well, as the vector of its first component ux times, in brackets, alpha minus beta uy, and the second component is uy times, in brackets, gamma ux minus delta. That is a Cauchy formulation of the problem, and we can apply our results on the existence and uniqueness of solutions by analyzing this function f in the right-hand side of the Cauchy problem. So let's try to do the Peano existence theorem. We have got u prime of t equal f of t u of t, with the function ftu being ux times alpha minus beta uy in the first component, and uy times gamma ux minus delta in the second component. We start at time t0 equals 0, and with the initial vector, let's call it u0 equal x0, y0. To apply the Peano existence theorem, okay, we need to pick some time t1 larger than 0, which means larger than t0, and we also need to pick some radius rho. Well, for the time being, this can be completely arbitrary. Okay, we need to check where f is actually defined. Well, since f is defined everywhere for all possible values of t and u, certainly f is defined for all times t and vectors u, where the time t is taken from the interval from t0 to t1, and the vector u is taken from the ball of radius rho around u0. That's not particularly difficult, and we also see that f is continuous because every component of f is continuous. Okay, with that we have satisfied all the conditions of the Peano existence theorem, and we conclude that there exists a function u which goes from the interval starting at t0 up to some time tau. Tau is some time after t0, mapping into r to the 2, such that we have the initial condition satisfied. u0 is equal u0, and we also have the differential equation satisfied for all times from this interval. U prime t is equal f of t u of t, whereas the time t is between t0 and tau. So if I think of the solution as a trajectory that goes through the space r to the 2, starting at u0 in this graphic here, then at least for some time the trajectory is actually defined. It is still possible that the trajectory develops a singularity, that it blows off to infinity in some direction in finite time, or maybe the derivative becomes infinitely steep. Maybe the velocity of this trajectory becomes infinitely large. It is all still possible. The Peano existence theorem does not guarantee us the existence of the solutions for all times. But anyways, the Peano existence theorem does not guarantee us the uniqueness of the solution, and for that we need the Picarlinolf theorem. We only need to check one more condition, namely that there exists t from the interval between t0 and t1, and all vectors u1, u2 taken from the ball of radius rho around u0. We have the inequality, as usual, that the distance of ft_u1 and ft_u2 is bounded from above by L times the distance of u1 and u2. To prove that inequality, we need a moderate amount of work. So let's write down the left-hand side of the inequality. That is the Euclidean norm of a vector. The first component is u1x times alpha minus beta u1y minus u2x times alpha minus beta u2y. And the second component is u1y times gamma u1x minus delta minus u2y times gamma u2x minus delta. Now to proceed, we regroup the terms in each component. So this Euclidean norm is equal to the Euclidean norm of the vector with first component alpha times u1x minus u2 minus beta times u1x times u1y minus u2x times u2y. And the second component is gamma times u1x times u1y minus u2x times u2y minus delta times u1y minus u2y. This is the same Euclidean norm of the same vector. I've only regrouped the terms in each component according to the coefficients that appear, according to the coefficients alpha, beta, gamma, and delta. If I take a look at this last Euclidean norm, I recognize that in the two components, I have similar looking terms associated with the different coefficients alpha, beta, gamma, and delta. So I regroup the coefficients, and if I multiply the second component of the vector with -1, which does not change the Euclidean norm, then I see that I've got two terms associated with alpha and delta, which look very similar, and two terms associated with beta and gamma, respectively, that look very similar. So to estimate this Euclidean norm from above, I apply the triangle inequality. So I get that this is bounded from above by the norm of the vector with components alpha times u1x minus u2x, and second component delta times u1y minus u2y, plus the Euclidean norm of the vector with first component beta times u1x times u1y minus u2x times u2y, and second component gamma times u1x times u1y minus u2x times u2y. So we've got the sum of two Euclidean norms, and we estimate each of those separately. On the left, we see that actually this is already the Euclidean norm of the difference u1 minus u2, except that the first and second component are scaled by numbers alpha and delta, respectively. And it's easy to see that this Euclidean norm can be bounded from above by the maximum of alpha and delta times the distance of u1 and u2. So that part already looks quite good. Now let's move on to the second Euclidean norm. If you take a look at this Euclidean norm involving terms associated with constant beta and constant gamma, you see that actually each of the two coordinates of that vector of which we take the Euclidean norm is the same if it weren't for scaling by beta and gamma. So similar as before, we can factor out the maximum of beta and gamma to get an upper bound, so that Euclidean norm is bounded from above by the maximum of beta and gamma of the norm of the vector with first component u1x, u1y minus u2x, u2y. And the second component happens to be the same. Since we take the Euclidean norm of a vector with identical components, okay, that Euclidean norm is equal to the square root of 2 times the absolute value of u1x times u1y minus u2x times u2y. And I suggest to you verify that identity by yourself. Okay, now we have the product of the two components of u1 minus the product of the two components of u2. In order to get the type of inequality that we want, we do a little trick. Namely, the trick is called adding a zero. So the last term is identical to square root of 2 times the absolute value of u1x times u1y minus u1x times u2y plus u1x times u2y minus u2x times u2y. Here in the middle, I've added the term u1x times u2y, and I've subtracted the term u1x times u2y. That does not change the absolute value, but now I can apply the triangle inequality. So that term is bound from above by the square root of 2 times u1x times u1y minus u1x times u2y plus square root of the absolute value of u1x times u2y minus u2x times u2y. As you can see, in the first absolute value, I've got the difference of two terms with common factor u1x. And in the second absolute value, I've got the difference of two terms with common factor u2y. And I can factor out these two factors and bound this from above by square root of 2 times the absolute value of u1x times the difference u1y minus u2y plus square root of 2 times u2y absolute value times the absolute value of u1x minus u2x. Okay, certainly this can be bound from above by square root of 2 times the maximum of absolute value u1x and absolute value u2y. Now multiplied with the absolute value of u1y minus u2y plus the absolute value of u1x minus u2x. In this last term, I've got the difference of u1 and u2 in the y-coordinate plus the difference of u1 and u2 in the x-coordinate. Each of those can be bounded from above by the Euclidean norm of u1 minus u2. So I get this all is bound from above by the square root of 2 times the maximum of u1x and u2y in absolute value times 2 times the Euclidean norm of u1 minus u2. Now, summarizing this all, I get that for everything altogether, I've got the upper bound namely the Euclidean norm of u1 minus u2 with the following coefficient in front of it. The maximum of alpha and delta plus the maximum of beta and gamma times 2 square root 2 times the maximum of u2y. This almost looks like the inequality that we want, except that in this large the coordinates of u1 and u2 appearing. So this large coefficient still depends on u1 and u2. As a remedy for that, we use that by assumption u1 and u2 are contained in a ball of radius rho around the initial vector u0. you want to get rid of these occurrences of U1 and U2. Now, since U1 has maximum distance rho from U0, I know that the absolute value of the x-coordinate of U1 is at most the absolute value of the x-coordinate of U0 plus rho. And similarly, since U2 has maximum distance rho from U0, I know that the y-coordinate of U2, an absolute value, is at most the absolute value of the y-coordinate of U0 plus rho. Now, to simplify things, I know that the x-coordinate and y-coordinate of U0 can be bounded from above by the Euclidean norm of U0. So I get, in the last step, the following coefficient in front of the distance of U1 and U2, namely the maximum of alpha and delta plus the maximum of beta and gamma times 2 times square root 2 multiplied with the Euclidean norm of U0 plus rho. All that together gives me a constant L. And this eventually shows the inequality that I need for the Picarlinolf theorem. So the important thing is that this constant L here does not depend on the time from the interval t0 up to t1. And it does not depend on the vectors u1, u2 taken from this ball of radius rho around u0. So what I find is that the solution starting at time t0, going up to some time tau, is indeed unique. Now, we would also like to prove the existence of a unique solution that actually is defined for all times using this global existence and uniqueness theorem. However, the problem is that this constant L still depends on the radius rho and the norm of the initial condition. And as you can tell, as rho and the norm of u0 get larger and larger, so does the constant L. So with that technique, we do not get this constant L uniformly bounded for all times t and all vectors u1, u2 taken from all of r to the 2. Indeed, you can actually show that there's no such constant L defined for all time and all vectors u1, u2 taken from the two-dimensional Euclidean space. So unfortunately, we cannot use the global existence and uniqueness theorem to show the existence of a solution for the Lotka-Volterra system. One can actually show that the function f for the Lotka-Volterra Cauchy problem does not satisfy the requirements for the global existence and uniqueness theorem. Suppose we study the Lotka-Volterra system for 40 units of time. And we start with a prey population of 4 and a predator population of 6. And suppose that the coefficients alpha, beta, gamma, and delta are 1.0, 0.1, 0.1 and 0.4 respectively. These two graphics here illustrate the type of dynamics that you're going to observe. On the left, you see a plot that depicts the predator and prey populations over time. The blue curve is the prey population, and the orange curve is the predator population. So what you recognize here is that the Lotka-Volterra system is indeed periodic. So you see that first the predator population goes up, which causes a decline in the prey population. And as the prey population goes down, the predator population declines as well. Then, since the predator population has declined, the prey population recovers, and eventually there's enough food for the predators so that the predator population recovers again. And that cycle repeats on and on. Now let us take a graphic on the right. There you see an x-y coordinate system, and the x-coordinate corresponds to the prey population, and the y-coordinate corresponds to the predator population. In fact, here you see different solutions for the Lotka-Volterra system with the same parameters alpha, beta, gamma, delta, but with different starting populations. Each of these lines here corresponds to a periodic solution of the Lotka-Volterra system. In fact, one of these lines corresponds to the evolution of the Lotka-Volterra system that is depicted in the left part of the graphic. Namely, we remember that started with 4 units of prey and 6 units of predators, which puts us into this part here of the coordinate system. And what we see here is that first the populations go up again, but then as the predator populations are too large, they reduce the prey population, and the prey population goes down. Eventually also the predator population declines, and the prey population begins to recover. So if I take the x and y coordinate over time for the Lotka-Volterra system, I can draw a trajectory throughout this xy plane here. Where, so to speak, different choices of starting populations put me on different trajectories here throughout the xy plane. As you can tell, there's a family of curves here corresponding to different starting populations. And it seems somehow that these curves are kind of centered around a particular point. In this case, it is the point with prey population 4 and predator population 10. X equal 4, Y equal 10. It turns out if I happen to have the predator and prey population precisely at this point, then the Lotka-Volterra system is stable. There's no more variation in the predator and prey population. They remain constant over time. And if I'm very close to this equilibrium point, then the predator and prey populations will vary only a little bit over time. There will only be small fluctuations. Remember that we had such a closed curve also for the harmonic oscillator, and that curve corresponded to an energy level that remains constant throughout the evolution of the harmonic oscillator. That was a conserved quantity of the harmonic oscillator system. And perhaps it is surprising that the Lotka-Volterra system, which is motivated not from physics but from biology, we have a similar conserved quantity.